We begin with the tutorial for the problems. Let us proceed with the theory behind how to solve or synthesize a mechanism when different types of inputs are given. We have different kinds of information. So there will be two main different types of problems. The first one is without prescribed timing, and the second one will be without prescribed with prescribed time. So in the first case, that is without prescribed timing, we have a freedom to choose our points a1, d1 as well as the crank length, that is a1, b1. But in the prescribed timing method, we have only our choice to choose the points a1, d1, but we do not have the choice to fix our crank length a1, b1. That will be given by the problem that we have to find out from the given data. So let us understand some basics first. So let us say this is our 4-bar mechanism a1, b1, c1, d1, where a1, d1 is fixed. So the crank can move like this, and this can also rotate like this, and the b1, c1 coupler link also has a degree of freedom. Now I'm gonna fix a rigid triangular plate to the coupler link b1, c1, and I'm calling the point e1 as the coupler point. Now let us give small rotation to the crank shaft, the crank a1, b1. The point b1 will move in the path of a circle with radius a1, b1 with the center as a1. Let us say the new position of b1 is this, that is b2. Since d1 will be the same, we have to find the location of the new location of c1, that is c2. It is nothing but it is very simple to find it. Just draw an arc from b2 with length of b1, c1. Draw an arc, and from d draw an arc of length b1, d1, c1, and this one. So this will meet somewhere. So meet it here, somewhere over here. So we have our C2, B2, A1, D1, that is our new position of the 4-link mechanism. Since it's a rigid triangular, this is a rigid triangular plate, it is very easy to construct it. Okay, the same way we can take arc lengths and cut it from B to C2 with the radius of B1, E1 and C1, E1 respectively, and this will be our new coupler point E2. So whatever construction I have done till now basically is represented in this figure A. That is initially it is A1, B1, C1, D1, and the coupler point is E1, and when it is given a rotation about point A, the B1 moved to B2 and C2 moved to C2, D1 is fixed, D1 is fixed, and this dotted lines are the new positions of this 4-link mechanism. Okay, let us look at this 4-link mechanism with just a small inversion. So initially I considered the link A1, D1 to be fixed, but what if the link B1, C1 is fixed? That is, the coupler link is fixed. So all the 3 coupler points, that is E1, how many coupler points you may take, that is E1, E2, E3, so on up to En, they will be at the same location, that is E1, initial position, and B1 will be at the same position, C1 will be at the same position. There is no movement. There is only movement is present only in A1 and D1. That is A1 will take A to A3 and D1 will take D to D3. So consider the 4-bar link mechanism again, fixed at the coupler link B1, C1. Since the whole triangle is rigid, so there will be no movement in any of the part of the triangle. Now let us rotate the point D1 about C1. It will trace the arc of circle. So this is the new location of D1, that is, and we know the length A1, D1, so it will be same as A to D2. So cut an arc across here, and from B1, A1 also is fixed, so cut an arc from here. So A2 will be somewhere over here, so it is clearly seen. The new positions of the links are clearly shown here. So when I just rotated the D1 about C1, this link moved like this, and the link A2, A1, B1 moved to a new position A2, B1. So the figure B here shows very clearly what I have drawn just now. So initially it was at A1, B1, C1, D1, and now it was given some rotation. The C1, D1 has shifted to C2, D2, C1, D2, and B1, A1 has shifted to B1, A2. Now we are going to make an important observation from this steps. Consider the quadrilateral A1, B2, C2, D1 and A2, B1, C1, D2. So from this two, it can be very clearly, easily shown that the triangle B2, E2, D1 and triangle B1, E1, D2. So triangle B2, E1, D1, B2, E2, D1 and triangle B1, E1, D2 are very similar, are in fact congruent triangles here. In fact, this can be generalized more. That is, in fact, if there is another point D3 and another coupler point E3, then it can also be shown that triangle B3, 3D1 and is equal to is congruent to triangle B1, E1, D3. So this is the basic theory part behind the synthesis of that 4-bar links. Now let us look how to synthesize a 4-bar link without prescribed timing. Usually E1, E3, E2, E3 will be given in the problem. So once they are given, you have to plot them on a graph like this. So E1, E2, E3 are plotted. Once they're plotted, we can choose this point as A1, and somewhere outside here we can choose a point D1 on the same line joining these two. So I already told you that we don't have to choose any fixed length for the crank. So any length for the crank can be chosen. So initially I will mark some length of the crank B1 somewhere at can be at any location, and the corresponding points B2, B3 are also plotted, and also D1, D2, D3 are plotted, and we will discuss this in further in detail when we take up a problem. Once we have our D1, D2, D3, we know that the center C1 lies on the intersection of these mid-normals of D1, D2 as well as D2, D3. So in case of a problem with fixed prescribed timing, that is if the crank length is has to be fixed by us, it is fixed by the problem, we need to find the crank length. How to find out the crank length or the crank position B1 will be discussed in the next problem. Once the crank length is found out by us, the same procedure has to be repeated as in the case of in the problem without prescribed timing. We are going to discuss our first problem. The first problem, we were told to design a 4-link mechanism, and we are also given the 3 position points of the coupler points, and like their polar coordinates are given, and also the angular displacements of the input links are given with the positions that are in respect to position 2 with respect to 1 and position 3 with respect to 1. So let us begin. So the first step is to locate the points E1, E2 and E3. For that, a coordinate axis is drawn, and then a reference point is chosen. Let us say the point is A1. Okay, so all the points, these all these 3 points correspond to E1, E2 and E3. So as I told you before, those are the polar coordinates of the points E1, E2 and E3. So it's very simple to locate them. So E1 has a radial distance of 55 meters from the reference point and an angular position of 75 degrees with respect to the horizontal. So just first mark a line that is 75 degrees. Okay, line that is 75 degrees, and which is at a radial distance of 55 mm. So this will be E1. So similarly, if you point E2 and E3, they will somewhere be here, lying around at 50 degrees and at 40 degrees. So once it is constructed according to the given polar coordinates, the points E1, E2 and E3 will be somewhat like this. So this is our current system of points E1, E2 and E3. These are also called as coupler points, as I already mentioned. So the next step of the deriving the synthesizing the mechanism is to rotate these this particular points E2 and E3. We were given theta 1 2 and theta 1 3, right? So we have to rotate those these E2 and E3 counterclockwise so now the next step is to rotate 2 as well as 3, that is this line as well as this line according to the given data. So now we will be rotating in the clockwise direction, that is this direction. This is by 30 degrees, theta 1 2, and theta 1 3 will be 70 degrees. So if we add 40 degrees plus 70 degrees, it will be 110 degrees, that is obtuse. So it will be somewhere around here. So the new positions of the points E2 and E3 will be somewhere around 50 plus 30, that is 80 degrees. E2 will be somewhere over here with the same radial distance, and E3 will be somewhere over here, let us say E3 dash and E2 dash. So now we have successfully declared where the points corresponding to the transformation. So now let's join this. So we also know that the line has to I mean the point, the coupler link B1 has to lie, it has to lie on the perpendicular bisectors of the line joining E1 E2 dash and E2 E1 E3 dash, right? So the green lines here denote the perpendicular bisectors of both the lines E1 E3 dash and E1 E2 dash. So they made it somewhere over here. So this point will be our B dash. Okay. So if we join O B dash, O is nothing but you have our A1 here. So A1 B1. So we found out our first coupler link. So let us proceed to the next step. So what we are looking here is the cleaner version of what I have drawn on the whiteboard. So here we can clearly see B1 is on the it's on the perpendicular bisector of E1 E3 dash and perpendicular bisector of E1 E2 dash. So they both intersect, and we know that it lies on both the perpendicular lines. So it has to be at the point of intersection. So thus we have located B1, and we also have fixed our A1. So now we have to proceed and find the other points C1 and D1. As we've already discussed in the theory part of this video, that we need to use the properties of congruent triangles to find out the other 2 points, that is C and D. So we are also given the angular spacing between the no, this is not phi, this is theta. So we are given the angular spacing between the lines, the various positions of the crank shaft that is to be inputted. That is initially the crank A1 B1. So the end point of the crank is at B1. That is the first input, and the second input with respect to the position of 2 with respect to 1 is at angle of 30 degrees. So go clockwise 30 degrees. Why clockwise? Because we've already since E2 E3 E1 are those are the coupler points which lie on the rigid triangle, right? As we discussed earlier, is it rigid triangle BEC. So this is rigid. So since the whole part of the triangle is rigid, so if we take a rotation about a point, so for example, how much E rotates about this point, let us see if it rotates theta, and so B also must rotate theta, so that there is no angular deformation of the body, then only we call it rigid, right? So that is about it. And similarly we have to go 70 degrees in order to meet the point B3. So we are going 70 degrees. So we went 70 degrees. This is B1, and we have to draw locus of a circle. Locus of a circle is drawn. I mean, locus of point B1 is drawn, which is a circle. So it looks somewhat like this. So at these angular positions, draw a straight line, and the point where it intersects, it is B2, and the point where this intersects the locus, it is B3. Okay, it is B3 and this is B2. Now we have completed various locations of the input crank input. Now we'll use the congruent triangle property to find out various points of D, that is D1, D2, D3. So we'll use the first congruent triangle property, that is triangle B1 E1 D2 is equal to triangle B2 E2 D1. I fixed my D1 as here for our convenience. So our triangle B2 E2 D1 will be this, marked in blue color, same as the same color here, and we have B1 E1 here, that is marked in red color, which is the, let us say, the base of the triangle B1 E1 D2. So since these two triangles are congruent or similar, we just have to replicate a triangle B2 E2 D1 with bases B1 E1 D1 with bases B1 E1. So for that it is very simple. Take the length of E2 D1, and from the point E1 take the length E2 D1 and cut an arc, and from the point B1 take the length B2 D1 and cut an arc. The point where both of them intersect is our location D2. Now this is our triangle B1 E1 D2. Now we have another set of congruent triangles with us, that is B1 E1 D3 and B3 E3 D1. I'm going to erase the rest of the construction so that it will be easy for us to So here we have our D1, here we have our D2. Our goal is to find D3 using D1, B2, sorry, B3, B3, E3 and B1, E1. Let us construct B3, E3, D1 first. This is B3, E3, D1, which is same as the color green here also. So this is the base B1, E1 of B1, E1, D3, which is congruent to B3, E3, D1. So in the similar fashion, if we draw arcs from B1 and E1 to find out D3, so our arcs will intersect somewhere over here like this. After joining, it will look somewhat similar like to this, and this is our D3. So this is not to scale, this is just for representational purposes only. Now we have all the points D1, D2, D3. Finding out C is simple, C1. So we know that it lies on the intersection of the mid normals of the lines D1, D2 as well as D2, D3. So these are the normals and they intersect somewhere over here. So this will be C1. Now we have A1, B1, C1, D1, which is nothing but the required 4-bar link mechanism that has been constructed from the given data. Here will look somewhat very similar to this A1, B1, C1, D1, and as the crankshaft moves, that goes to B1, B2, B3, and as I told, E2 is, since it lies on the rigid triangle, it is always E2 is here, E1 is here, E3 is here. Similarly, various locations of C are shown, C1, C2, C3. So that's the end of this tutorial for this problem. Next problem. This is also called as a 3-point synthesis method for a 4-link mechanism. Basically, in this case, we will know 3 different positions of the output. So from that, we will find out the where the location of input crank is, and we will construct the 4-link mechanism. So here we are given theta 1 2, theta 1 3, phi 1 2, phi 1 3. Phi corresponds to output, theta corresponds to the input shaft. In the previous example, I have already mentioned what is the meaning of theta 1 2, theta 1 3. The first step is fixing the link AD. Then we will choose a convenient length for the output crank. So C1D1, C1D, the output crank in this case. So phi 1 2 is 50 degrees and phi 1 3 is 80. Now let us rotate the point C1 to point C2 by 50 degrees and C1 to C3 by 80 degrees clockwise. So the positions are like this. So here theta 1 is 35 degrees and theta 1 3 is 80 degrees. Now we have to rotate C2 and C3 with respect to the point A by this given amount in anti-clockwise direction. First let us rotate AC2 in the anti-clockwise direction by 35 degrees. Let us say the rotated point is C2 dash, which is rotated by 35 degrees. Now let us rotate AC3 in the anti-clockwise direction by 80 degrees. It will come somewhere over here. Let us say it is C3 dash, that is rotated by 80 degrees. Now we have located C1, C2, C3 as well as C1, C2 dash, C2, C3 dash. Let us erase all the other stuff and only highlight the points. So we have C1, C2 dash, C3 dash, and we have here D, and here we have A. Now we have to find B. So the point B1 lies on the intersection of the binormals of line C1, C3 dash as well as C1, C2 dash. This is the line C1, C2. This is the line C1, C3 dash. I have drawn their perpendicular bisectors. Their perpendicular bisectors meet at this point. So this point is B1. Now we have our 4-link mechanism AD, C1, B1. Let us join all those and say A1, A, B1, C1, D is our required 4-link mechanism. That is the end of this problem. Now let us look at the third problem. There is a slight modification here. We are given a slider crank mechanism, which is just an inversion of 4-bar mechanism. As usual, theta 1 2, theta 1 3 are given. We already know what are those. Theta corresponds to the input crank. Here the 4th link is modified by a sliding pair. So we are given the distances in terms of distances S1 to S13. Now I'm telling the difference between theta and S. S denotes the displacement of the slider in the slider crank mechanism. When S12 is given, it is nothing but the displacement, the distance between the position 2 and position 1, that is 40 mm here, and S13 is nothing but distance between position 3 and position 1, that is 96 mm here. Also there is an eccentricity, which is nothing but an offset, which is the amount of height that the slider is above the horizontal line containing the point A. So the given data is noted down here. So let us begin. The first step is to draw two parallel lines with an offset of 20 mm. Let us fix a point A anywhere on the baseline, and then choose any point C1 on the line that is offset from the horizontal line, horizontal baseline, and then C2 and C3 are marked, since you already know the distance between 1 and 2 as well as 2 and 3. So please note that the diagram is not to scale, it is just for representational purpose only. So the lines are very clearly shown here. Let us join AC1 and AC2 and AC3. So now we have the line segments AC2 and AC3. Let us rotate the line segments AC2 and AC3 by the amounts theta 1 2, theta 1 3 respectively, that is 30 and 60 degrees respectively. This is the new position C2 dash corresponding to C2, and this is nothing but 30 degrees. So this is the position C3 dash of C3 when rotated about an angle of 60 degrees. We have now located the point C2 dash and C3 dash. Now let me erase all other points that are not required here, and also the lines that are not required. So this is the representation containing only points C1, C2 dash and C3 dash and C2, C3 dash. Now let us join C1, C2 dash as well as C2, C3 dash. Now we know that the point B will lie on the binormals, intersection of the binormals of the line C1, C2 dash and C3, C2 dash. This is the binormal of C1, C2 dash. So they intersect somewhere over here. Let us say that is B1. Remember that the word binormal is nothing but just a perpendicular bisector. It's just a fancy word for perpendicular bisector. We found out our B, so our slider crank mechanism will be A B dash C1. I am joining A B dash AB1 C1. So this is not to scale, this is just for representation purpose only. If you draw very carefully, then you with the same procedure you will get accurate results. This is the end of the video.